for those speakers who are willing to. It'd be great to have you come back with your video and audio. I've tried to sort of summarize some of the questions that have been asked already on Slido, but if anyone who's listening sort of has general questions for all the panelists, feel free to throw them in Slido. But one question that sort of come up in different ways for different speakers is thinking about observational or training data for these models. And you all work in sort of different niches across the field of aquatic sciences. And I'm curious from everyone, what would you say is limiting the implementation of these models in terms of having that training data?
I would just say, and I think Charu will probably add to this, it's just like there's harmonizing data. There's a lot of data out there, but harmonizing and getting it together in a trustable, analysis-ready data set is just a vast, horrendous. That was the last slide I got to, which is basically like harmonization sucks. And that's why we don't have this stuff as much. So, Aquasat uses Google Earth Engine and JavaScript and all that, but it was probably like 6 months of harmonizing the water quality data and 2 or 3 months of learning Earth Engine and implementing all that. The hard part was the harmonizing. So I think getting, at least on the water quality side, getting everything in the same place with the same annotation and the same all that stuff is just really hard. And I think Charu probably has more to add.
Yeah, we had this discussion. I mean, I absolutely agree that harmonization is a pretty big challenge, and that's partly why I didn't even, I'm collaborating with folks from the USGS who've done all that hard work and just using their data set. It's partly why I made that call for fair data, because there is data out there. It's not curated in a way that we can use as benchmark data sets. The Aquasat, and there's camels, and there's all these things starting to emerge that I'm seeing becoming very popular de facto benchmarks. But I think we need to be thinking about, how do we fund some of these efforts just to build these benchmark data sets that we need. So like the ImageNet sort of equivalents, the MNISTs for our aquatic sciences. I also want to say that, in general, like for instance, streams and rivers, they're like we've heard all throughout today, they're not monitored at the frequency we really want. So there's a very small fraction of streams that have been monitored. And so, in what we've been thinking about is in some of our projects, this concept of co-design, which I didn't talk about today, but how can we use these models to inform where the observations are being collected? And there are opportunities, especially with the USGS funding some next generational water observing networks, to see whether we can start to use some of these models, like in the Delaware Basin, to inform perhaps where the next measurement should be going. So that's another thought. We should be talking with the field folks to be seeing how we can synergize with them to collect the data that can help the models.
Great. I don't know if anyone else has any other thoughts on that topic. Robert, this question came up during your talk, but it was thinking about scaling up, and how do you scale up when, or in scaling up, does that bias of regionality cause problems when you're training on sort of temperate lakes? How do you scale up to kind of other systems? And that might be thinking about observational data and it being biased to certain aquatic systems.
Yeah, that's a good point. I mean, we didn't do the scaling up yet, so this is a problem for the future me. But I mean, the model is really simplified that we are currently using. So we hope, because we have all these parameters and they are more black boxes. So now we're doing all this data exploration using machine learning to understand which equations we have to include that make the model more robust for scaling up. But this could potentially be a problem if we only build models for the US Midwest, and then we want to apply them for some other place. Then yeah, there could be problems, but we really hope that the machine learning can pick up these signals that we are currently neglecting.
If I could jump in for a second, I think it relates very much to the previous question. which is how do we prioritize the kinds of ecosystems for which we get data? And so far the prioritization, as Matt pointed out, is systems that we're monitoring for water quality, purposes. But maybe we should be emphasizing big gradients that we feel are important to understand sort of underlying process in the system. And and I agree, probably a lot of those data are out there, but the harmonization and munging effort required to make those data usable is sort of insurmountable without either help from federal agencies who already kind of have this, at least in part, on their plate, although water quality kind of falls between the cracks, actually, of a lot of federal agencies, or other funding efforts.
Yeah, so getting back to sort of scaling up, and Jared, in your talk on transfer learning, one of the questions that came up was, is there potential for these models to be overfit to sort of the training data set?
Yeah, so that is possible, but given how the meta learning is constructed, you could think that some of that is taken into account just because your training data for the meta model is based on transfer, and if it's overfit, those models won't transfer well during the training set.
So it seems like a pretty good approach.
Yeah, I think one idea we can explore is like I think Jared previously mentioned this, even if it overfits somehow, but then if we only use this meta transfer learning model, the base model as a base model when we adapt to a new place, but then we allow some fine tuning using a few amount of true observations from another basins and other systems, and then it's possible to just adjust the model to better fit the new scenario. And that's, I think, another thought.
Also, model agnostic meta learning is a whole framework that kind of does that, and it tries to specifically find models that are adaptable to a lot of systems, and that's the goal of it. So that's another way of doing that.
So one thing that I'm not sure if it came up in anyone's talks, but was sort of I was thinking about was this switch from sort of traditional just process modeling to machine learning. And there's, with process models, there can be a huge time investment in calibrating them to a specific site. And that calibration effort can stretch on for months to years. And so while it seems sometimes simple to implement a process model, it can be really time consuming and difficult. And so how do you view using machine learning models actually as sort of a time-saving application, rather, on top of being potentially more accurate and more transferable?
Yeah, I think machine learning has a lot of promise in this use, because not just in aquatic science, but also in some other domains. Because we always want to generate data at very high resolution, but running these physics-based or process-based models at this higher resolution is always very time-consuming. So that's why people usually do a lot of approximation to generate data or simulate data at much coarser resolution. But using machine learning model definitely can provide a lot of promise there. I find there, I think Jared when Jared do this survey paper, I think we found several existing research that people just generate a few amount of simulation data at higher resolution, and then they train a machine learning model and use that machine learning model as a surrogate model to replace physics-based models to generate high resolution data. And that's basically considering the time cost of directly running this process-based model. I think there's a lot of promise there in this area.
Yeah, I want to add to that, sort of saying that we are taking a similar approach with our California groundwater example and trying to simulate a hydrous model. I think that was part of our motivation for even building a machine learning model like this, kind of physics-based model, even if it exists, like the Central Valley models have been like decades of investment to get them running and working right, and the dynamics are constantly changing, so that's a challenge. And within a year, actually, we were able to, if the data are available, within a year, we were able to get a machine learning model up and running and actually doing predictions out to a year, which is pretty fantastic in terms of how we could actually get there so soon. So that's, I do think it shows a lot of promise. The challenge is whether we have the data.
Any other comments on the time investment of machine learning that you've all spent lots of time on?
Oh, did I interrupt somebody? No, okay. So this is more about the time investment for the numerical simulation. And just emphasizing your point, Hilary, that sometimes it'll take a graduate student really a full year to get a hydrodynamic water quality simulation running for one system. And, I think there's a good argument to be made for the student learning a lot, in the process of getting that up and running. But on the other hand, they're way over parameterized. And so it does leave you wondering how much of the underlying process you really are learning about. And, it's sort of a general question in my head for those, especially, who've had a more experience in the KGML world. What are the trade-offs between using a fairly complicated simulation model as your process input, versus one or two or three very simple models that are really easy to spin up to help you? And I don't know if there's an answer among the group. But.
Definitely trade-offs.
Yeah.
All right, so in our last 5 minutes, this is a question that I'm hoping everyone might have an answer to, but I'm guessing we have a handful of students out there listening who are interested in this field and sort of trying to get into it. And this is an emerging frontier in aquatic sciences, and it's not something that students are traditionally trained in. And there's few sort of course opportunities to learn about machine learning in domain sciences. And so, if you're a student stuck at home for the next semester and have some spare time, what would you recommend dabbling in terms of learning some new tools and skill sets that might help you out? And you don't have to be a student stuck at home. You can be a emeritus professor stuck at home.
I would just say, like, find a play example. Like, that's low. It's not necessarily your dissertation, but it's just something that you can spin up to try to learn. I mean, whether it's Python, it's probably Python if it's if you're going to be doing any of the sort of more neural net stuff. Just finding a way to play around and find any of these data sets. Charu mentioned camels. That's a good one if you want to predict discharge. Just some data set that's already curated and is just ready to go, and you can just start playing around with learning these things. I think it starts. I'm trying to learn some of this LSTM modeling, and that's where I'm going to start. So I think just making sure it's play and maybe not embedded in your work just yet if you're starting out, because it takes a long time to sort of get there.
Yeah, I want to add that I think the platforms these days are so, computational platforms are really easy. Starting to work with TensorFlow or PyTorch, whichever is your favorite one. It's really easy to get spun up with a few lines of code. It didn't used to be the same way 10 years ago. You have to do everything yourself. Here, with a few lines of code, you can get these models running. I think it's the subject matter sort of expertise and really thinking about how you construct the problem, what kinds of data you want to use. This is why going with a pre-existing data set is kind of fun. And I'd say, there's a lot of work, especially that's starting to emerge, which has the data and codes that are already being published online. So that's a good place to sort of try to replicate something to just get started.
And I think for people who develop this method, like for ourselves, I strongly suggest that if possible that we can share, or if we can release all these codes and data sets to the public, because like if I just read the papers, I may easily get confused with like how to implement the physics-based laws without knowing details about these things in Python. And I think that would be very helpful for people who just want to get started on this project.
I see everyone nodding, Xiaowei. I think we all learn well from reading other people's code, so thank you in advance.
Yeah, just to add to that, I think this came up a couple times too, that it, not only is it the code, but also the hyperparameters that go into many of these models require some thought and experimentation. So including methods that we used to reach the choices that we made could be useful.
Great. Well, if there's no other closing comments from our panelists, I just want to thank you all for speaking. That was a really enlightening group of talks. This is recorded, so hopefully it'll be available for everyone to watch again when you want to go back and remember the details. Just want to also say that this was day one of our KGML workshop. So there's a full day tomorrow, starting with hydrology at 9:30 a.m. Central, and weather and climate in the afternoon. And all those talks are available. The set of talks is available on the website. So we hope to see you there tomorrow as well. So thanks, everyone.
Thanks, everybody.